So from the Schrodinger equation, we get the answers. And the answers are wave functions. Or orbitals. That's what we call them. For the hydrogen atom, how many answers do we get? In other words, for the hydrogen atom, each of these is the allowed state for the electron. And so how many allowed states are there for electron in a hydrogen atom? It turns out, well, a lot. In fact, there are going to be an infinite number of allowed states. And the first allowed state is the n equals 1. That's going to be the lowest. At the highest energy, we'll have n equals infinity. And from the Schrodinger equation, you know, the answers are going to be equations themselves, mathematical equations, because if you're going to write an infinite number of answers, you might as well look for some kind of pattern in those answers and represent the answers as a mathematical equation. And that's what we do here. And so when you look at the algebra, and we're not looking at the algebra, but when you look at the algebra, n can only have certain values, 1, 2, all the way to infinity. It has to be an integer value. If it's not an integer, it doesn't solve the Schrodinger equation. So for example, 1.1 wouldn't work. You know, since 1.1 doesn't work, then it's not an answer, and therefore it's a forbidden state. And so when we look at the number of allowed states, how many are there? They're an infinite number. If there are an infinite number of allowed states, then what's forbidden? Because if everything's infinitely allowed, then is there anything that's forbidden? Yeah, it turns out, yeah, there's plenty. For example, 1.1 is forbidden, but n equals 2 is allowed. And so this kind of looks like the hydrogen atom. In fact, when we come up with the answers to the Schrodinger equation looks like this. It's h bar psi is equal to E psi. And so when we come up with the answers are going to be here, you know, the orbitals and the energy. The hydrogen atom and one electron species, we'll see that the energy just depends on one thing, and that's n. And therefore, we call n the principal quantum number, or the energy level. And so E sub n, well, for the H atom, it's just going to be Z minus Z R sub H over, is this Z squared? Actually, I can't remember. Z or Z squared over n squared. Sometimes n squared. And so over here, we look at the energy. The energy is going to be pretty much the same. This is going to be minus R sub H. This is going to be minus R sub H over 2, etc. And so what's different? If the energies look the same, we get this same spacing where, you know, this is going to be 0. Minus R sub H would be 2.178 or 9 times 10 to the minus 18 joules. 2.179. So what's different? Well, the interpretation of these energy states is different. In the Bohr model, these energy states corresponded to orbits. In the quantum mechanical model, which the Schrodinger equation is the foundation for, we interpret these differently. Instead of having orbits, we know that these are orbitals. And so using the quantum numbers, which we talked about, the restrictions on the quantum numbers, did I write them all up here before? We're going to have n, l, and m. And so each of these orbitals is going to be given a n, l, and m value. And those n, l, and m values are restricted mathematically. So for example, L can equal 0, 1, dot, 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 up to a max of n minus 1. And it takes on all the values up to there. M just ranges from minus L, dot, 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 through 0, dot, 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 to plus L. And so with these, we can figure out what's going on. For multi-electron species, the energy is different. For multi-electron species, the energy depends on N and L. And so N, we think of N as being the energy. L, we think of L as being the shape of the orbital. And M is the orientation and the number of the orbitals. And so let's take a look at what these mean. And so we started generating the quantum mechanical energy level diagram for the H atom. And we saw it's different than the Bohr. And basically, the lowest energy state is going to have an n equals 1. When n equals 1, then the L values are going to be 0 up to a max of n minus 1. So the L value here is going to be 0. When we have a 0 L value, that's what we call an s orbital. And the m value here is just going to equal 0, plus 0 to minus 0. And so this is what we call a psi 100 orbital. And so what is a psi 100 orbital look like? Well, it's going to have a certain energy. And so the energy is just dependent on 1. And so we have that. So this is minus r sub h. And we want to know where is that electron. So we have the energy, and we pinpoint the energy. The energy is minus 2.179 times 10 to the minus 18 joules. We pinpoint the energy. What does that say about the position of the electron? If we pinpoint the energy, then the position of the electron is certain or uncertain? In other words, remind me what the Heisenberg uncertainty principle is. What is the Heisenberg uncertainty principle? The Heisenberg uncertainty principle says that there's a fundamental uncertainty in terms of energy and position. So the uncertainty in the energy and the uncertainty in the position combined has to be greater than or equal to some quantity, h over 4 pi. And that means if the uncertainty in the energy is minimal, then the uncertainty in the position is got to be big to compensate for it. And so when we think about the position of this, well, this is what it looks like. We make a plot of psi, and then we look. Psi for 100 wave function looks like this, where this is going to be the nucleus here. And this is the distance from the nucleus here. So there's kind of a peak here, and it drops off. That's what the wave function looks like. To interpret this wave function, we square it, and so we get psi 100 squared. Psi squareds are probabilities. And so by squaring this, well, it's going to pretty much look the same. Just the y values will be squared. And so this will be probability. And so this is how we're going to interpret this orbital. If I draw the nucleus here, let's say the nucleus for the hydrogen atom, then the highest probability for the electron is right next to the nucleus. As I get further and further away, the probability drops off. The probability is going to continue dropping until it hits 0 probability, but it won't hit 0 probability until we get to r equals infinity. And so psi squared approaches 0 as r approaches infinity. And so there's a minuscule probability that it can be found, the electron can be found very far from the atom. But it's minuscule. And so when we visualize this, we can visualize it using electron cloud. Electron cloud is going to show the greatest density of dots right next to the nucleus. And then the density of the dots is going to decrease. This is kind of like the bird analogy. We're trying to pinpoint the position of the bird. And so the further and further away we get, the lower the probability, but there's still a slight probability it could be quite far from the nucleus, like that. And so this will be the psi squared 100 representation here in terms of electron dot density. But what this is this is a psi 100 or 1s orbital. Okay, that's one way of visualizing this. Another thing's done, although it's not really apparent in this case, is whenever we square something, we lose some information. Like for example, if you took the square root of 4, what's the square root of 4 equal to? Plus 2 or minus 2? Well, which is it? Is it plus 2 or is it minus 2? Well, you don't know, right? Because you've lost that information. We call that phase information. And so when we square something, we lose the phase information. To keep track of the phase information, we look. This is what we call positive amplitude here. And so if this is positive amplitude, then this square came from the positive, squaring a positive value. And so we put a positive there to indicate the phase of the wave that we just squared. So sometimes in the orbital we'll do that as well here. All right. It's hard to represent orbitals as clouds. So we could use little styrofoam balls like this to represent the orbital. So this would be the representation of the orbital. But, you know, it's hard because how big of a ball do you make? How big of a ball do you make? Well, in order to capture all the dots, we'd have to make an infinitely large sphere. But what happens is the probability drops so low that, you know, when we hit a certain point, there's very little probability it's outside there. And so what we typically do is we typically get like 90 or 95% of the area under the curve and call that the size of the orbital. And so if we do that, let's get 90 or 95% of the area. If we get 90% of the area under the curve, then that means there's only a 10% probability it's outside this. And so we can have something called 90% boundary, in which there's a 10% probability the electron's outside this, but 90% it's in this. And so that means, you know, from here to infinity is just only 10%, and 90% it's in this smaller volume. And so this is a 1s orbital. Drawing this 90% boundary, you can draw a line here, and represent that like this. This is not the greatest drawing, but this would be the 90% boundary. It's not a real boundary. It's not a real wall or anything like that. It's just a border in which 90% of the dots are contained, 10% of the dots are outside. Okay. We'll just call it 90 or 95% boundary. This 90 or 95% boundary will give us an indication of the size of the orbital. The next orbital that's allowed is, well, we don't have any other L values that are allowed, so we have to jump up to n equals 2. That's the next one. For n equals 2, then the first L value that's allowed is L equals 0. L equals 0, M equals 0. And so this would be a psi 2, 0, 0 orbital here. Psi 2, 0, 0. Psi 2, 0, 0 is also called a 2s orbital. And so here we had a 1s orbital, here we're going to have a 2s orbital. Okay, what does a 2s orbital look like? A 2s orbital is going to be higher energy. And so higher energy means that it's going to be a bigger orbital. That is, the electron can be found further out from the nucleus. And so if we plot the psi 2, 0, 0, it looks something like this, where this would be the nucleus, and it actually drops down and goes up. Okay, not to scale, it's going to be bigger than the 1s. The 1s would be a lot smaller. For example, the 1s would be something like this. And it's symmetric on both sides. 1s would be quite a bit smaller. No, that's not very visible. All right, but an interesting thing happens because here we have positive amplitude, here we have negative amplitude. Now, in terms of probability, we square it because is it possible to have negative probability? No, the lowest probability we can have is 0 probability. And so if we do a psi squared 2, 0, 0, what's going to happen is this. Well, this is going to go up. Something like that. Not very symmetric. Try to make it more symmetric. Okay, we lose the phase information, and so this part came from squaring the positive amplitude. This part came from squaring the negative amplitude. And it's going to be a positive probability to find these. And so we retain the phase information by just using these signs. Why do we need to know this? We need to know the phase information because of waves, how they interact. Are we getting positive amplitude with positive amplitude, or positive amplitude with negative amplitude? If you have positive amplitude with negative amplitude, they tend to cancel each other out. And so we need positive and positive, and negative and negative. Those are what we call constructive interference waves. And so we keep track of this phase information because it depends on, later on when we look at chemical reactions, we've got to look at how the waves interact. Well, anyway, going here, this is an interesting thing because here we have 0 probability. In fact, there's 0 amplitude here and there's 0 amplitude here. If we have an area of 0 probability, we call that a node. There are actually 2 nodes here. There's a node here, which goes all the way around. And then there's going to be one more node at r equals infinity, because at r equals infinity, the probability goes to 0. And so nodes are regions of 0 probability. And so if I'm looking at a 2s orbital is bigger than a 1s orbital, and then we have something called a node inside there. And so if I look at the electron cloud of a 2s orbital, the greatest probability is going to be closest to the nucleus. So the most dots will be here. If we get farther, the probability of the density of dots decreases until we hit the node where it goes to 0. There's no dots at the node. And then we have some probability outside the node. So this would be a 2s orbital. A 2s orbital, the electron for a 2s orbital can be in the same volume of space as the 1s orbital. Because the 1s orbital is right here, you know, let's do it in green. Do the 1s in green here. The 1s is a smaller orbital. It's not going to be nearly as big. So this would be the 1s orbital here. It's just that when we look at the 90% probability boundary now, the 90% probability boundary for a 2s orbital is going to be a lot bigger. And so looking at the probability, the 90% boundary is going to be out here, let's say. Whereas the 90% probability boundary for 1s is in here. And so 2s orbital is quite a bit bigger. The 90% boundary. All right, that's the 2s orbital. I don't have a bigger styrofoam ball than that one. You'll have to use your imagination. What's next for the allowed orbitals? N equals 2, L equals 0. And when N equals 2, L can also equal 1. And 0 is an s orbital, well 1 is a p orbital. That's the shape of that. And we have 3 m values. You know, m equals -1, m equals 0, and m equals 1. Here, here, here. And so this would be a psi 2, 1, -1, psi 2, 1, 0, and a psi 2, 1, 1. Sometimes we'll give letter designations. For example, 2px, 2py, 2pz. I'm showing the orientation of those. When we look at the wave function for, let's say a 2, 1 orbital, like this, 2, 1, 1, something. It's going to look like this, where be like this, where there'll be 0 amplitude here, positive amplitude here, negative amplitude here. Then we'll square this to get the probability. So we'll get psi squared 2, 1, 1, which is going to look like this. Not doing the greatest for drawings, but right. Now this lobe, actually it should be bigger. This lobe comes from squaring the positive. This lobe comes from squaring the negative. But in terms of probability, both are positive. We can't have negative probability. So if we were to look at a cloud, you know, electron cloud, it's going to look something like this. Where we'll have what we call a lobe here on one side, and a lobe here on the other side. So it has this shape. Two lobes. So this is essentially it. If we look at the 90% boundary, it's going to have this kind of dumbbell shape. The 90% boundary, you can just draw solid lobes. So this would be the px here. This is the py here. Py. Px, py. They look exactly the same. They're just orthogonal to each other. and then the PZ sticking out. So we got 3 p orbitals. Like this. Px, py, pz. Okay, one of the interesting things is this. The energy of the 2p orbitals is exactly the same as the 2s. And so all 3 2p orbitals have the same energy as you'd expect because they look exactly the same. It's oriented orthogonal to one another. But you wouldn't have expected the 2s to have the same energy. And so we call this degenerate, or energetically degenerate. Degenerate just means they have the same energy. And so the p orbitals have the same energy, and the s and the p orbitals have the same energy. So they're all degenerate orbitals. Why would they have the same energy? Well, they have the same energy, even though, you know, the cloud looks totally different. If you were to kind of average out the electron and just say, you know, this whole cloud averages to an electron this distance from the nucleus. And then you look at the 2s and you say, this whole cloud averages out to an electron at this distance. The average distances are the same. In fact, the 1s orbital would have kind of an average distance of about 53 picometers. In other words, the first Bohr orbit. The 2s orbital has a distance of n squared a naught, which is 100, 200, 212 picometers, the 2s orbital. It turns out the 2p orbitals, even though they have a totally different shape, if you were to average this out over 3 dimensions, the average distance of the electron would be 212 picometers. And so they both have the same effective distance from the nucleus, you know, when you normalize it over a 3-dimensional sphere. Okay. And so that's the 2p. Here we can see a pattern emerge. And the pattern emerges is you look at the total number of orbitals. How many total orbitals do we have here? 1. How many total orbitals do we have here? Well, 1, 2, 3, 4. 4 total orbitals. Do you see a mathematical pattern related to n? So far, I'd like to say, you know what? There are n squared orbitals. N squared orbitals for each m. So 1 squared is 1, 2 squared is 4. So let's see if this pattern holds. There's another mathematical pattern. Maybe you can see it here as well. When L is equal to 0, we have 1 orbital. When L is equal to 1, we have 3 orbitals. Can you come up with a mathematical equation that describes this pattern? So when L is equal to 0, we have 1 orbital. When L is equal to 1, we have 3 orbitals. What's the mathematical pattern? For each L value, there are blank orbitals. For each L value, there are blank orbitals. I'll give you an equation here. This is the same kind of thing, you know, the Schrodinger equation. In the Schrodinger equation, you got these algebraic equations, and you look, okay, for the n, you know, and then just kind of simplify it to some simple pattern what we got. N plus L. N plus L, yeah, that works. N plus L doesn't work because N is 2, L is 1, so that's 3. I got 4. close, but good try. It doesn't work. Try to think of some other mathematical equation. See, sometimes we solve things not to an answer. We don't say those three orbitals there. Sometimes we solve things to an equation, and that equation is much more powerful because we can predict. Well, you might not see the pattern just yet. Let's go to the next energy level. We call these energy levels. So for example, n equals 1, that's the first energy level. N equals 2, that's the second energy level. And then the next energy level is n equals 3. N equals 3, all of these orbitals, interestingly, are going to have the same effective distance, which is n squared a naught, which is 9 times a naught, so 9 times 53, whatever that comes out to. But the first one is, okay, if n equals 3, then what are my L values that I'm allowed? I'm allowed L equals 0, which is the s orbital. I'm allowed L equals 1. I'm running out of space here. L equals 1, which is the p orbital. And I'm allowed L equals 2. L equals 2, what kind of orbital is that? It's a d orbital. When I go to this, if L equals 0, then M equals 0. Here. See, all these are the same energies. M equals 0. And so this would be 3, 0, 0. Because when we do this, we do psi m L m. And so this would be psi 3, 0, 0. And we call this a 3s orbital. Interestingly, a 3s orbital has 2 nodes in it. Yeah, so if we're looking at 3s orbitals, it's going to look something like this, as far as the wave function goes. The wave function is going to go up, it's going to go down, and then converge to 0 here. And so there's one 0 amplitude point, a second 0 amplitude point here, which means when we square 0, it comes out 0, there's 0 probability. These are 2 nodes here. In other words, the 2 nodes, do you see a mathematical pattern? How many nodes did we have in the 1s orbital? Internal nodes. How many internal nodes did we have? Was there 0 amplitude? Well, only 0 amplitudes at infinity, right? And so it didn't really cross. It was just positive amplitude. And so for the 1s orbital, there were no internal nodes. For the 2s orbital, the 2s had what we call a spherical node, Like we had an inner sphere and then an outer, and a node separating the two. The 2p orbitals have what are called planar nodes, right down the center. This plane, there's 0 amplitude here. There's 0 probability. We're finding that. One of these is positive amplitude, the other is negative amplitude. We just put a plus here and a minus here to show that for the wave function. And so n equals 2 has 1 node, n equals 1 has 0 node, n equals 3 should have how many nodes? N equals 3 should have 2 nodes. And so when I look at a 3s orbital, the 3s orbital is a lot bigger, 3s orbital, but inside the 3s orbital there's a sphere of 0 probability at that point, and a second sphere, 0 probability, 2 nodes in there. So there's a figure in your book showing that. Do you see a pattern? What's the pattern? No? Mathematical pattern. All right, think about about it. So we have three p orbitals, three 3p orbitals. So this is a 3, 1, negative 1, 3, 1, 0, and 3, 1, 1, where m is equal to minus 1, m is equal to 0, m is equal to 1. Those are our m values here. Three px, 3py, 3pz. These are going to have two nodes, actually, the 3p's. The 3p's are going to be a lot bigger than this. And the two nodes that it's going to have is it's going to have a planar node here, and then another internal node here and here. So a total of two nodes, a total of two nodes. And then we have L equals 2. If L equals 2, then our m values are minus 2, minus 1, 0, 1, and 2. And so we get a total of 1, 2, 3, 4, 5 orbitals. 5 orbitals. That's the easy way to do it. If you want to figure out how many orbitals are there for a given L, just count them. 1, 2, 3, 4, 5, right? Or we could use some kind of mathematical equation. Do you see a pattern now? When L equals 0, there's 1. When L equals 1, there's 3. When L equals 2, there's 5. What's the math? Give me an equation that represents this pattern. So for example, if I had L equals 5, I could figure it out. If I had L equals 5, I go minus 5, minus 4, and then just count them, right? Or I could look for the pattern. The pattern is there are 2L plus 1 orbitals for each L. And so if L equals 2, that's 2 times 2 is 4 plus 1. In other words, we got 2 here, and you got to add the 0. And so that's 2L plus 1. That makes sense? So 2L. And as far as the nodes go, there are n minus 1 internal nodes. N minus 1 internal node. And so these p's looks very similar. You know, these are the 3p orbitals. These are going to be the 3d orbitals. The 3d orbitals are going to be cut by two nodes. Let me show you. So these are the d orbitals here. The d orbitals are cut by two nodes. There's one planar node here along this plane and another planar node horizontally here. So these are the two nodes. When you have these two nodes, it slices it into 4 lobes. These are lobes. This is one orbital with 4 lobes. We have, this is called the DZY because the lobes are in the ZY plane. This is Z axis, the Y axis, ZY plane. This is the XZ because this is the X axis and the Z axis. So the orientation would be like this. Here's the YZ, would be like this. The XZ would be like this, along the nucleus. This is the XY. It's like this. The XY plane, Z sticking out, this. So here, this is normally the way you'd look at it. X here, Y here, and Z sticking out. If you look at all these have the lobes between the axis. So between the axis here and here, the lobes are between the axis. This one, the lobes are directly on the axes. And so this is y-axis, the x is missing, and the y. And since the lobes are directly on the axis, it's a little different than these other three. This is called the dx squared minus y squared. And so, you know, for these orbitals, we have other designations. Put my pen.
N2 and N1 is just in between, somewhere in between the, like, you know, you have the models?
Mm-hmm.
It would be in between. Or where?
M2?
No, N2 and 1.
N2?
N1. So the energy level, the previous energy level would be still in there.
Yeah. Yeah, exactly. All these are overlapping.
Yeah.
Let me show you. So these orbitals here would be on top of this. The n equals 1 you can't see because it's inside here. And so the 1s orbital's inside. This sphere is the 2s orbital. It occupies the same space as the 1s orbital. In fact, the 1s orbital and 2s orbital can be right next to each other. 2s orbital can actually be closer to the nucleus than the 1s orbital in one instant of time. And so just because we know the position of the electron in one instant, we don't know, is that a 2s electron or a 1s electron? What is that? You know, because we lose that information. If we pinpoint the position, do we know the energy? We don't, so we don't know the identity of that electron, per se. Unless we knock it off, and it's going to cost us some energy to knock it off. We could figure it out. But do you see these lobes sticking out? You know what these are? These are the p orbitals. So we have 3 of them. One, like this, along the z-axis, has 2 lobes. X and the y. You know, yeah. And so X, Y, Z. And then you got to throw these on top, and so you'd have other lobes sticking out of this. And then pretty soon it gets kind of messy because everything's overlapping on top of each other. And so they're still there. Uh-huh.
So the orbitals there, the ones that kind of are on the axis itself, overlap the P?
Yes.
Like engulf it?
Yes, right. Engulf the P's. Yeah. This one on the axis is going to completely engulf. Let's line up the axes here. Here. You see? It's going to totally overlap. D orbitals are a little bigger in terms of the 90% probability boundaries than P's. And so it completely engulfs it, the D's. And so there's a lot of overlap. And then here, there's one more D. There are 5 D orbitals. This one's a little funny because it looks like a P orbital with a hula hoop on it. Uh-huh.
So when we talk about like P orbital, are we talking about the exterior of it, like that line, or everything from the outside?
Everything, the whole thing. The exterior, this line is the 90% boundary. But if you were to do the dots would all overlap. Yeah. Well, we could show that here. I'll show that later. And so, yeah, they'd all be overlapping, you know, but they'd have different energies. Between these. All these orbitals here, all the n equals 3 orbitals are actually the same energy. And so the 3p orbitals are equivalent in energy to the 3s, which are equivalent in energy to the 3d. Now the 3d are kind of big, but you know they have a kind of a big volume as well. But they all have the same effective distance. We'll get a better idea of what I'm talking about effective distance later. They all have the same effective distance, so their interaction with the nucleus will be the same. All right, this is also a d orbital, but this one doesn't have two planar nodes. This one has conical nodes. A conical node here and a conical node here. And so these cone nodes. We have this d. You don't have to do this, but you know, we could. For example, label this 3px, 3py, 3pz. The native 1, 0, and 1 have some orientation, but off the top of my head, I don't remember how we define the coordinate system for that. So 3, 1, 1 might be the x, and 3, 1, 0 might be the y, and 3, 1, negative 1 might be the z, but it doesn't really matter because we're not going to do anything with that right now. And so this one, we have 3dxy, 3dxz, 3dyz, 3dx squared minus y squared. And this last one, with the two cone nodes, is called a z squared. And so that'd be 3dz squared. But those letter designations, don't worry about it. You aren't expected to know those until Chem 1B. Then you'll have to have them memorized. Okay. But we aren't. So by following these mathematical patterns, you know, we aren't actually solving the Schrodinger equation. We know that the answers to the Schrodinger equation follows these mathematical patterns or restrictions. And so by following this, we can, you know, we can generate the entire energy level diagram from n equals 1 to n equals infinity. It just take a lot of time. And so let's just pick one energy level and figure out all the orbitals that might contain. And so if I go from n equals 1 here, n equals 1, that's, you know, that's pretty easy. It's just the 1s orbital. Let's go to n equals 5. At n equals 5, how many orbitals am I dealing with at n equals 5? Each n level has how many total orbitals? Look at the pattern. Do you see it? How many orbitals did n equal 3 have total? Count them. So n equals 1 had 1 orbital, n equals 2 had 4 orbitals, n equals 3 has 9 orbitals. So what's the mathematical pattern? N squared. And so they're n squared. So n equals 5 should have how many orbitals? 25. 25 is reasonable. If I said, let's figure out all the orbitals for n equals 100, n equals 100 would be 100 squared orbitals. You know, 10 squared squared would be 10,000 orbitals. Is that reasonable? No, that's too much. I wouldn't give that on a test. But 25 orbitals, that's pretty fair, I think. N equals 6 would be 36. 36 might be pushing it, you know, because that's can take up a lot of space, right? But it's not difficult to figure out, because if n equals 5, then what are my possible L values? L equals 0, L equals 1, L equals 2, L equals 3, L equals 4, L equals 5. Tell me when I should stop. L equals, well, I should stop now because I ran out of room, but should I write L equals 6? Continue it down here? No. Is this good? We'll stop at L equals 5? Yeah? Should we stop at L equals 5? Well, maybe you know, because L equals 0 is called an S, L equals 1 is called a P, L equals 2 is called a D, L equals 3 is called A. F. L equals 4 is called A. G. L equals 5 is called N. H. And so what we're dealing with, we're dealing with the 5s orbitals, the 5p orbitals, the 5d orbitals, the 5s orbitals, the 5g orbitals, and the 5h orbitals. Is that right? Yes? No. What's wrong? What did I do? You know what's wrong with it? Too many L's, right. What's the maximum L value I can have? The maximum L value is n minus 1. Well, n minus 1 is 5 minus 1 is 4. This is the max. I can't go beyond that, so 5H is not allowed. 5H is forbidden because of the Schrodinger equation. It would not solve the Schrodinger equation. Well, when L equals 0, I only have one M value, M equals 0. And so we call this the 5, 0, 0 orbital. I'm going to get rid of the psi because it takes up too much space. When L equals 1, then I'm going to have 3 orbitals, 2L plus 1, right? And what are those 3 orbitals? They're going to be the 5, 1, negative 1, 5, 1, 0, 5, 1, 1. In other words, the 5px, 5py, 5pz. When L equals 2, I'm going to have 2 times 2 is 4, plus 1 is 5. So 5 orbitals. 1, 2, 3, 4, 5. And what are they? They're going to be the 5, 2, minus 2. M goes from minus L to plus L. And so this is going to be 5, 2, minus 1, 5, 2, 0, 5, 2, 1, and 5, 2, 2. This is going to be the dxy, dxz, etc. When L equals 3, how many orbitals do I have? Well, the two ways to determine. You could use the mathematical equation 2L plus 1, or you could just figure it out. It goes from minus 3 to plus 3. We'll figure it out the second way. So if it goes from minus 3 to plus 3, then it's going to be 5, 3, minus 3. And then, try to save room here. 5, 3, minus 2. And then 5, 3, minus 1. And then 5, 3, 0. And then 5, 3, 1. 5, 3, 2. And 5, 3, 3. And so that's 1, 2, 3, 4, 5, 6, 7 orbitals. And so the 5F have 7 orbitals. The 5G are going to have how many orbitals? So let's do the 5G. G is L equals 4. So 2 times 4 is 8 plus 1 is 9. And so there should be a total of 9 orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9 orbitals in the 5G. We call this a sublevel. This is the n equals 5 level. The n equals 5 level is going to have how many sublevels? Do you see the pattern? I forgot to write this pattern in the morning. There are blank sublevels for every n level. I'll let you tell me what the equation is. How many sublevels do I have? A sublevel would be the S sublevel, the P sublevel, the D sublevel. Each of these are separate sublevels for that level, one level. And so what is it? There are how many sublevels for every level? N minus 1? There are n minus 1. And so that means if n equals 5, I should have 4 sublevels. Well, 1, 2, 3, 4. Actually, I have 5 sublevels. So remodify. When n equals 3, how many sublevels did I have? When n equals 3, I had 3 sublevels, the 3s, the 3p, and the 3d. And so there are n sublevels for every n level. And so we took 5 sublevels here. G. What are the orbitals? There are 2l plus 1 orbitals for every sublevel or for every L. And so what are they? There's 5, 4, minus 4, 5, 4, minus 3, 5, 4, minus 2, 5, 4, minus 1, 5, 4, 0, 5, 4, 1, 5, 4, 2, 5, 4, 3, 5, 4, 4. So we just derived the 25 allowed states for the n equals 5 energy level. It wasn't hard, was it? You know, even 36 wouldn't be that hard. N equals 6. Actually, and that should be fine. 36 orbitals is not hard. What's after 36? 49? 49 is easy, but it just takes up too much space. All right, so what we have here is a difference. In the Bohr model, the Bohr just said we have the n equals 5 orbit, right? In the quantum mechanical model, the electron can be in the n equals 5. If it's in the n equals 5 here, it could be in any one of these orbitals. These are all allowed. And if this electron in the n equals 5 drops all the way, not maybe to here, not to the ground state, which is the lowest energy here, but if it drops to the 2s or the 2p, then a 5 to 2 n equals 2 transition emits, this is red, green, this emits blue light. Blue light. And so if an electron is in one of these orbitals here, one of the 25, and drops down to one of these orbitals here, one of the 4, then we get a blue photon emitted. And this is one of the lines in the hydrogen atom spectrum. And so in a lot of ways it looks similar because it's just an n equals 5 to n equals 2 transition. It's just, you know, it's just not one orbit. It's 25 different orbitals that we have here. Okay. There are other restrictions in the electron jumping from one orbital to another. It has to do with angular momentum, but we aren't going to get into that. All right. This is for like the H atom. If we do something like the He plus ion, helium normally has 2 electrons. If you knock one of them off, then it'll be 1 electron. And so the difference here is H atom has 1 proton and 1 electron. The He plus ion has 2 protons and 1 electron. So if you have 1 proton and 1 electron, the electron is going to be attracted to the proton. What happens if you double the number of protons? Is that going to change the attraction? You know, so now I have plus 2. What's going to happen to the attraction for the nucleus? Is it going to increase, decrease, or stay the same? Well, if you have twice the positive charge, the attraction increases. You know, pretty much the attraction doubles. If the attraction's doubled, it's going to pull the electron closer. And so in an H atom, the 1s orbital looks like this. In an He plus ion, the 1s orbital is a lot smaller. The 1s orbital is a lot smaller because having 2 protons, increasing the positive charge, we call it Z, increasing Z is going to pull in the electron closer. It pulls in the electron closer, and that means an H atom might have an energy here, but the closer the electron gets to the nucleus, the lower the energy is. And so in an He plus ion, the 1s orbital is actually quite a bit lower in energy than an H atom. And so the H atom might be up here, the He plus is going to be here. And that goes for all the orbitals. And so in another 1 electron species like He plus, the orbitals are going to be smaller and lower in energy than the hydrogen atom. And so if we go to Li2 plus, Li2 plus is going to have exactly the same diagram, except the orbitals will be smaller than the ones in He plus and the ones in H, and they're going to be lower in energy because the closer the electron gets, the lower in energy it is. The further electron gets, the higher in energy it is. Okay, that's pretty much for the 1 electron species. For multi-electron, it's different. And so let's take a look at multi-electron species here. For multi-electron species, the energy depends on N and L, the shape. Okay, let's compare 2 orbitals. For single electron, let's look at a 2s orbital versus a 2p orbital. A 2s orbital for single electron, let's look at a hydrogen atom. This looks different than a 2p orbital. And so, since the shapes are different, you expect the energies to be different, right? I would expect the energies to be different, but what you do is you figure out the most probable distance, something called the most probable distance, which you would think the most probable distance is the place with the highest probability, but it isn't. The most probable distance is somewhere here, about 212 picometers. And the same thing here is if you average this over 3 dimensions, like a sphere, and normalize it over 3 dimensions, we see the same most probable distance. And so, in other words, the effective distance is the same. That is, this normalized here over 3 and this normalized over 3 dimensions over the entire sphere is going to give you the same effective interaction between the electron and the nucleus, which is going to dictate the energy. And the energy is going to be dictated. The farther the electron is from the nucleus, the higher the energy. The closer it is to the nucleus, the lower the energy. And so this is why the 2s and the 2p are same in energy. But that only works for single electron. When we have multi-electron, then they're no longer the same in energy. For multi-electron, the 2s turns out to be lower in energy than the 2p. Energy. And that has to do with something called shielding and penetration. So let's take a look at the lithium atom. See what we're talking about here. Lithium has 3 electrons. And I have to. Do you know how many electrons the nucleus holds? None. How many electrons does 1s orbital hold? 2. And so in a 1s orbital, let's draw the 90% boundary of this 1s orbital. There's going to be 2 electrons. Now, if you look at each electron, each electron is going to see a +3 instead of a +1. So that means a 1s orbital in lithium, is it going to be bigger or smaller than a 1s orbital in hydrogen? So here, you look at the 1s electron. It sees +3. This 1s electron sees +3. Both electrons are seeing +3. Is it going to pull in the electron tighter or looser or the same as a hydrogen nucleus? The same? No? Maybe I should write something here. Do you guys remember Coulomb's law? From week 1. Anybody remember Coulomb's law in the first week class? The force of attraction is proportional to the charge on A, the charge on B, divided by the distance between the center of charges squared. Does that sound familiar at all? And so let's call B the electron. So the charge on the electron is -1. Let's call A the nucleus. And so in hydrogen, it's +1. But in lithium, it's +3. Assuming the distance is about the same, then lithium is going to have 3 times the attractive force as hydrogen. And so there's going to be a 3 times stronger pull on the electron than in hydrogen, which means the electrons are going to be pulled in very close to the nucleus in lithium. And what that means is this. The 1s orbital in lithium is like this, whereas the 1s orbital in hydrogen is like this. In other words, the 1s orbital in hydrogen is a lot bigger because it just doesn't pull in the electron as tightly. And it's going to be higher in energy because the average distance is going to be farther. Whereas the 1s orbital in lithium is going to be lower in energy and it's a lot smaller. But that's beside the point. The point is this. Why is the 2s and the 2p different in energy? So I have 2 electrons here. Now I got to add a 3rd electron. Should I put the 3rd electron in the 2s or should I put the 3rd electron in the 2p? And the 3rd electron goes in the 2s, not the 2p. Because going in the 2p, it'd be higher in energy. And so let's do the dots. A 2s orbital is bigger than a 1s orbital. It's higher in energy. The greatest concentration of dots will be near the nucleus. And so a 2s electron can be right at the nucleus, just like a 1s electron. But its effective distance is going to be farther out. 2s orbital also has a node, right? So there's some kind of node here. A node is a region of 0 probability. You know, 0 amplitude gives 0 probability. And so we got a 2s like this. That's a 2s. Versus a 2p. 2p electron is going to look like this. Now, this is a 2p. Now what we're interested in is something called Z. What is Z? Z equals 3, right? So each electron wants to see the Z equals 3 because that's going to lead to the strongest attraction, right? Z equals 3. But the problem is this. If I put a third electron in the 2s, will the 2s see that plus 3? Does it have a clear, like a 1s electron pretty much just has a clear line of sight. Boom, it sees the nucleus. It's right there, right? But if you're a 2s electron, and let's say you're out here, what's going to happen is, well, you got these 1s electrons interfering with your view of the nucleus, right? In other words, they're blocking the view, or they're shielding the view of the nucleus from you. Does that make sense? Well, you run into the same problem if you're a 2p electron. If you're a 2p electron, then these 1s are screwing up the view. You want the 1s electrons to move out of the way so you can see the full 3 plus charge of the nucleus. But, all right, but because all the volume, it's all overlapping. And so another way is this. A 2s electron can sneak around the 1s electron and find itself very close to the nucleus. And so if a 2s electron sneaks around this, then it's got a straight shot at the nucleus. The 2p electron can do the same thing. If there's a 2p electron, it can try to sneak in here, right? Get a clearer shot of the nucleus. And so this is shielding, and this is penetration. Penetration is this ability for the electron to sneak in here and get close to the nucleus. Shielding is when you're out here and these other electrons are blocking the view of the nucleus from you. When an electron blocks the view of the nucleus from you, then you don't see the full plus 3, right? You see something called Z effective. And so if you're an electron out here versus an electron out here, you're going to see a different Z effective. Z effective is what we call the effective nuclear charge, which is going to be less than plus 3. And so Z effective for a 2s and 2p, they have a different Z effective. And so the Z effective here goes like this. The 2s are going to have a greater Z effective. The 2p are going to have a smaller Z effective. And the greater the Z, the more stabilizing this is. And so, here. In terms of Z effective. And so when we look at this, we can see this when we map out the wave functions. And so when we look at the 200 wave function, we see a 200 wave function is quite penetrating because there is a chance, the greatest amplitudes here, there's a chance that that electron can be right against the nucleus. Actually, I shouldn't do psi 200, I should do psi squared. What's the difference between psi and psi squared? Psi squared is what we call the, and psi is what we call the, what? Psi squared is a probability. So that's psi squared 200 to 2s. Psi squared 2p, oops. This is psi squared 211. Let's just go with a 211 orbital. This is one of the two p's. Now the problem is this. You know, in the one electron species, both of these orbitals have a straight shot at the nucleus. There are no other electrons blocking the view. But unfortunately, in multi-electron, you have the other electrons blocking the view. Well, what are the other electrons blocking the view? Well, one set of electrons that are blocking the view are the, what? Are the 100. These guys are blocking the view of the nucleus, the 100. The 100 are shielding the nuclear charge from the n equals 2 orbitals, the 2s and the 2p. So which one do you think is shielded more, the blue or the green by the red? Well, I'll tell you, what's shielded more of the green? What's shielded less of the blue? Which one has a higher probability of being close to the nucleus? Nucleus is right here. The blue or the green? The blue. And so this is what we say. The blue are more penetrating. That is, they can get close to the nucleus and less shielded than the green. The green are less penetrating, because look at the probability of finding it close to the nucleus is close to 0. And more shielded than this. And so you can see it here, the blue can easily be found close to the nucleus, whereas the green, this pinches off here, this pinches off here. This is a much lower probability. It's going to be right next to the nucleus. And so the result is that the greater the nuclear charge, the lower in energy. The higher, in other words, we see this kind of pattern. For example, the 2s are going to be lower in energy than the 2p, because these are going to have a higher Z effective. That is a greater nuclear charge. They have a higher Z effective because they're more penetrating and less shielded than, they aren't going to see the full +3 because some of the +3 charge will be blocked. This is going to have a lower Z effective. Z effective is the actual charge at C. The 1s electrons will see a Z effective of pretty much close to 3, very close to 3. And so the way it's going to work is this. As the shape changes, as we go from S to P to D to F, what happens is S are the most penetrating. P's are more penetrating than D's. And then as far as shielding goes, P's are more shielded than D's, which are more shielded than F. So in terms of energy, this is what we see. This is for energy. given n, we're going to see that the energy is going to vary like this. S will be lowest in energy, followed by P, followed by D, followed by F, etc. And that just has to do with penetration and shielding. So we end up with a splitting of the sublevels. And so we end up here with 1s and then the 2s. The 2s and 2p for multi-electron are no longer going to be the same energy. The 2s are going to be lower in energy, just slightly, because they're more penetrating and less shielded. The 2p are going to be slightly higher in energy because they're less penetrating, more shielded. And so we lose this degeneracy here, that is the 2p is greater than energy than the 2s. And this repeats for the 3s. The 3s are going to be lower in energy than the 3p. And then finally, well, what about the 3d? Well, the 3d aren't very penetrating, and they're very well shielded. And so the 4s are more penetrating, so those drop down here. And the 3d are way up here because when you look at the psi-squared functions, there's a very, very small chance that they're going to be close to the nuclei. In fact, the 4p are right here. And so what we're going to see is that the energy levels are going to change. This looks like the same, the energy levels, but what we're going to call this is the first shell. Okay, this is going to be the second shell. Second shell is the n equals 2 energy level, but when we get to the third shell is missing one sublevel in the n equals 3 energy level, and that's the 3d. In the third shell, we only have 2 sublevels. Third shell only has 2 sublevels. The third energy level has 3 sublevels. And so this is just some jargon. And then, well, what happened to the 3D? The 3D went into the fourth shell. And so the fourth shell, well, there's some orbitals missing. Because where's the 4D and the 4F? The 4D and 4F went into higher shells. And so we see this splitting of the energy levels. And so this is why we're going to focus on these shells instead. First shell, second shell, third shell, fourth shell. Now, you should know this diagram to the fourth shell, and you should be able to draw it out to the fourth shell. But we can go further because it pretty much fits a pattern. The pattern here we can generate 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 5g, 6s, 6p, 6d, 6f, 6g, 6h, etc. And if we're trying to figure out the ordering of the energies, it goes like this: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, etc. And so this would be the first shell, second shell, third shell would stop here at 3p, fourth shell would stop here at 4p, fifth shell would, etc. And so we'll look at this next time, periodic table. So I got behind. Okay. Going slow.